Hey everybody, welcome. Today I am going to be talking about fugacity. So the objectives for my video are going to be to explain the equations for pure species, for finding the fugacity of pure species, and then for finding the fugacity of mixtures and solutions. The next thing I'm going to be talking about is using PVT to solve fugacity problems. So I'm going to be going back to things we did in the equations of state video. So using the things we've learned from equations of state and applying that to fugacity problems. And then the last thing I'm going to get into is assumptions. So the kind of assumptions we can make to make fugacity equations smaller and simplify them. And then I'm also going to get into assumptions for vapor-liquid equilibrium as well. So here I've just written out all the important things that we should know. So for ideal gas, real gases, solutions, and mixtures. So before I actually go through all the equations, I'm just going to clarify what all of these funky symbols mean that I'm talking about here. So F here is the fugacity of the species in interest. The next symbol is the fugacity coefficient. It's called the fugacity coefficient. And then our gamma here is our activity coefficient. And I have a video just on the activity coefficient. So ways that we can find a correlation for it if we're not given one. So you should check that out because you will need to know that. And then the last two I have, you can see that it's the F for fugacity and the same symbol as the fugacity coefficient, but they are the fugacity and the fugacity coefficient of a species in a mixture. That's what the little chapeau, the little hat on top, means. So like here I'll write fugacity, fug slash coefficient of species in a mixture. So whenever you see a hat, that means that I'm referring to mixtures. So that is the fugacity of the species in a mixture, okay? Which is not the same as the fugacity of just the pure species. So here, let me start with number one, ideal gas. So here on the left-hand side, I have 1, 2, 3, 4, 5, 6 rows. Okay, these are, yeah. So I don't have actually anything to say about that. So here I divide into 6 rows, and then once you've decided if you have an ideal gas, real gas, ideal solution of a gas, ideal solution of a liquid, mixture of a gas, real solution of a liquid, things like that, which you're going to be able to find out from when I talk to you about assumptions, which is later in the video. But once you've determined which one you have, then you can look here on the left-hand side of my table and decide if do you have a pure fluid or is it a mixture solution. Okay, well, I guess mixture solution is for my 3 to 6 over there. So for number one, I have ideal gas. So for a pure ideal gas, the fugacity of the ideal gas is going to be equal to the pressure of the system. So I don't know, if I have methane in a jar and the pressure in that jar is 5 atmospheres, let's say, then I'm able to assume that's an ideal gas, then that is the fugacity of the gas, okay? And then also you can say that the activity coefficient of an ideal gas, the fugacity coefficient of an ideal gas is equal to 1, okay? But then if you're looking at ideal gases in mixtures or solutions, the fugacity of an ideal gas in the mixture is going to be equal to the partial pressure. So the mole fraction in the vapor times the pressure, this right here, okay? Or we can call it, I think it's also called P star. You guys are going to call it, okay? Partial pressure. And the Fugacity coefficient, again, is 1, okay? But the Fugacity coefficient in the mixture, okay? That's very important. Notice here how I don't have that. They're different. They're different things, okay? Then number 2, if your assumption is going to be that you have real gases and you have a pure fluid, so just one species, then we're looking at Fugacity is equal to Fugacity coefficient times pressure. And if you have a mixture solution, the Fugacity of the component in the system is going to be the Fugacity coefficient of the species in the system times the partial pressure again, okay, of that species. Okay, maybe make this a little eye more visible. Okay, and then here for number 3 to 6, it's all solutions and mixtures, so you can forget about how I've divided it on the left-hand side. So same thing, you just have to look at what I've written you. Also, just be very careful of here what I've written about the states, okay? So I suggest when you're doing problems and things like that, like write on your equation sheet, like, okay, ideal solution, these equations here, these ones here, are for an ideal solution. Oops, let me just fix that. These here are for an ideal solution, but in the gas phase. And the one right under that is for an ideal solution, but in the liquid phase, okay? So these are important things that you've got to notice, okay? And here I've separated. So for number 3, I've separated. These are 2 different equations, okay? I've separated them by a comma, okay? Or assumptions, I guess you can just call them. And here again, I've separated this, okay? So always be careful on what phase you're dealing with. I'm not going to keep explaining because it's the same thing. Fugacity in the mixture, same thing. Again, it's just a matter of looking at the equations, okay? But just notice here for number 4, when I say ideal solution of a liquid, that my activity coefficient right here is 1. Okay, so that's something that we assume when we do have an ideal liquid solution. All right, using PVT to solve. So now we're going to kind of go back to what we know about PVT, what we've learned in our equations of state video. So here I'm going to divide this into pure species, and then I'm going to go into mixtures and solutions later on. So number 1 is pure species. That's what we're looking at for PVT. So equation 1 I've written for once you've decided, okay, I need to get some information on the Fugacity coefficient of a pure species. Then you can use this equation. So you're going to have to integrate. You're going to have to integrate Z here. So you're going to have some correlation for Z. So that correlation that you're going to have for Z is probably going to come, it's probably going to be given to you. And if it's not given to you, then you can use your virial equation to solve it, okay? So I'll write here, virial equation, which is Z is equal to 1, or maybe I'll write that in blue because it is an equation. So Z is equal to 1 plus BP over RT, okay? And this B here, this is a constant. Equation number 2, you're looking for your activity Fugacity coefficient. So that's e to the PRTR. So we already know how to find PRTR. Really simple. We just need to go to our table, find the critical pressure and critical temperature of a species. And if we're given pressure and temperature of the system, then we're easily able to find the P reduce and the T reduce, okay? And then the beta naught, beta 1, and omega. These, again, are things that we're going to find from our table. So the omega is right here in our table, okay? So there's a different omega for every species, and you're going to be able to find them here. So that's just a constant from your table. And the beta naught, beta 1 are going to be found using the Pitzer method. Okay, remember when we did that in equations of state? My equations of state video, this is what you're using. So you're going to need your T reduced and you're going to need T reduced. That's all you need. So you just basically need a temperature for your species because T reduced is T over T critical. So yeah, pretty straightforward for that. And then number 3, fugacity of a species in the liquid phase. Here you have fugacity coefficient saturated. Okay, so what the key thing you need here to know is that we're going to use the same equation as number 2, but we're going to modify it a bit. Okay, well, not really going to modify it, but I'm going to rewrite it here. For when it says saturated, the P reduced here, P reduced is equal to P over P critical. That P is going to be your saturation pressure, okay? So this is P sat. And where do I get P sat from? Well, we're going to go to our table and use Antoine's equation, okay? Which is this equation right here. So all you need for Antoine's equation is to know the species and the temperature. And then all your constants, A, B, and C, are standing right there in front of you, okay? So, yeah, you're going to need that. And then PSAT, Antoine's equation. And then here you notice you have e to the VIL sat. So where the heck do I get this from? Well, this is going to come from something called the Racket equation. So the Racket equation is as follows. It says that VL sat of the species is equal to V critical times Z critical to the power of 1 minus T reduced, then that to the power of 0.2857. Okay? So basically all you're going to need here is your T to get your T reduced, okay? So I'll write it again. T reduced equal to T over T critical. Where this is going to be a constant, this is going to be a constant, and this is going to be a constant, okay? So, oops, my little hand is getting in the way there. Not so little, actually. So, your critical molar volume and your critical Z are going to come from here. I'm going to put that in green, maybe. Here's your Z critical, your compressibility factor, and your molar volume critical. Okay? That's where you're going to find in your table. They're constants and they depend on what species you have. So yeah, not too difficult. Then P, PSAT, and RT. Okay? So these are the equations that are going to come in handy when you need to find fugacity of a pure species. These are the equations you're using, okay? And when you have to use PVT to solve. Okay, then if I have mixtures and I need to find the fugacity coefficient in a mixture, you notice here I'm gonna label my equations. That would be important. 2 and 3. So for equation 1, I've written that ln of the fugacity coefficient of the species in the mixture is equal to this integral, okay? And then right beside that, I've written that the partial molar compressibility factor is defined as follows, this partial derivative over here, okay? So you might be asking, okay, well, how the heck am I going to get this partial compressibility factor, okay? And the way you're going to get that is I'm going to write it down here. So this is me referring to equation 1. You're going to get that from your virial equation. unless you're given some correlation for your compressibility factor, okay? So if you're not given a correlation, then you're going to use your virial equation, okay? So you're going to say that Z is equal to 1 plus BP over RT. And the way you're going to find B, well, where B is equal to y1 squared. Again, this is the mole fraction of the species 1 in the vapor. B11 plus 2y1y2 B12 plus y2 squared B22. Okay? And then if you ask yourself, okay, where the heck do my B11s, B22s, this stuff come from? Where does this come from? Well, this comes from here. Okay, when I have multiple species, this is my equation 6 and 7. Here's my, B11, B12, B22, B12. Okay, so, yeah, and then, well, I'm actually going to get into that later. This is kind of late, but you calculate this like the same way you did for pure species, okay? But now we're just doing it for 2 species. So these equations here, number 6 and 7, apply for pure species also, okay? It's just you don't really have to use them. So yeah, so these here are things you're going to calculate, your B11, B12, B22, and that's from the next slide I'm going to get into. And then you're going to have your B, okay? So that's the first step. And then the second step is that you want the partial, okay? See, we notice we have this little line on top. We have a partial to do. So we're going to multiply, once we have our B, we're going to multiply this whole equation by n. Okay, so it's going to look something like nz is equal to n plus nbp over RT. Oops. RT. Not going to fit in there. T. Okay, pretend that's a T down there. Okay, then we can do the partial derivative, okay? So we're going to integrate it with respect to n of species I, okay? So if we're looking for species 1, then we're going to integrate with respect to species 1, okay? And keeping species 2 constant. And if we're integrating with respect to species 2, then we're going to integrate with respect to species 2 and keeping species 1 constant. Okay, so pretty straightforward. So this is the first thing. Second thing, do partial. And then for a binary mixture, you're going to see equations 2 and 3, okay? So again, we're going to use the Pitzer method to calculate these B's, okay? And I'm going to show you on the next slide how we are going to calculate these B's. So when you're dealing with multiple species, you're going to have to calculate your BIJs. So like BIJ, here, what am I doing here? Yeah, your BIJs for species 1, species 2, okay? And just to compare it, I'm going to show you. Here, we are finding beta naughts, beta 1s. Here, I'm going to circle in red right here. Beta naughts, beta 1s. We are finding those for when we were dealing with 1 species, okay? So now we're dealing with 2 species, so we're going to be using, we want to find the beta naught of the 2 species in a mixture. That's what we're interested in right now. So this is the equation you're going to use for when you have 2 species in a mixture, okay? So it's not too difficult. We're going to start with equation 1. So the omega, I guess we'll call it, of I species I and j together is going to be omega I plus omega j divided by 2. So here in green, I'm going to start circling what's a constant. So these are from the table, okay? We're going to get these from our table. I don't know if I put the table here. No, I didn't. Did I put it? Here, yeah, what I showed you before. There's omega, table B1, right here. Okay? Constant. Number 2, pressure critical of I and J. Z critical, that's from your table. That's a constant. V critical, that is a constant, okay? So now you're going to say, okay, how the heck do I get Z critical of I and J, okay? Z critical of I is in the table and Z critical of J is in the table. So to get it for I and J, you do equation number 3. You just add the one for I and the one for J and divide it by 2. You're just finding the average of them, okay? And then for the V critical IJ, it's a little bit different, but it's equation number 4 here. So here, I'll circle. These are constants, 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 okay? That are just found from the table. So actually, maybe for number 2, I shouldn't put those as constants because you've actually got to calculate it. V critical IJ and Z critical IJ. Okay. So yeah, here are your actual constants. And then for number 5, you're going to be saying, okay, well, how the heck do I get my T critical of species I and J to get my T reduced? Okay. Oops, I won't put that in. So here you're going to see your T reduced. We know T reduced is T IJ over T critical IJ. So to get your T critical IJ, you're going to do this equation number 5, okay? So not too complicated. This K that you see right here it's related to intermolecular interactions, related to IMIs, but usually it's set to 0, okay? So usually set to 0. Okay, so usually that's going to be given, like that will be written in the problem statement. Okay. Yeah, so not too difficult. This here I'll write maybe for equation 6, T critical IJ, that's from equation 5. P critical IJ is the same thing, but from equation 2. Beta naught IJ, equation 7, and beta 1 IJ is from equation 8. Okay, and that's to find your B11, B12, B22. Okay, and also know that B11 or B22 is the same thing as B1 or B2. So you can use the first equations I ever showed you of the Pitzer method. Okay, this is just used for finding your B12, B21 sort of thing. Okay, so next I want to get into assumptions. So when we're dealing with Fugacity equations, it's really, really important to be able to simplify the Fugacity equations because they are difficult. And if we can simplify them, it will make our lives much, much easier, okay? So one of the first assumptions is how do we assume that we have an ideal solution of gases? So if you look back at the first slide I showed of the equations under ideal solution of gases, and note the state. This is important, okay? Gases, not liquids. There are two assumptions you can say. You can say that the Fugacity coefficient of the ideal solution is equal to the Fugacity in the mixture is equal to the Fugacity coefficient of the species. So you know that this right here, the Fugacity coefficient of the species, is much easier to calculate than that of the Fugacity coefficient of the species in the mixture, okay? It's simply just equation 2. Okay? It's really, really simple to calculate. So if you're on a word problem or something and you're like, how can I make this assumption? What am I looking for? You're going to be looking for a phrase that says something like the chemical species are similar, okay? So if chemical species are similar. So that's the kind of phrase you're going to be looking for. If it doesn't explicitly say ideal solution of gases, you're looking for something that says, okay, I have gases, but these the solution that it's in, they're very similar, the species, okay? The next assumption you're going to make is if you have an ideal gas mixture, okay? So for an ideal gas mixture, you'll have the Fugacity coefficient of the ideal gas for a species in the mixture is equal to 1. That simplifies your life so much because you don't have to do everything I just showed you relating to PVT to calculate, okay? So when can you make the assumption that you do have an ideal gas mixture? It's when you have low pressure or a high temperature. Okay? These are the assumptions you're making, but you have to look for this written in the word problem. So if it says the pressure is really low or there's a really high temperature, but it doesn't say ideal gas mixture, then maybe you can make the assumption that, okay, it is an ideal gas mixture then. I'll make that assumption. And then another assumption is making assumption to say that you have an ideal liquid solution. So this simplifies your life so much because you're saying that your activity coefficient of a species is 1. So that means you can eliminate looking for a correlation, which is what I showed on my activity coefficient video, or having to deal with anything to plug in numbers into a correlation given to you, okay? So the way you can make this assumption is when chemical species are similar. Or unless it says, okay, we have an ideal liquid solution. But if it doesn't, then you're looking for something that says, okay, you have liquids in a solution and the species in that solution are chemically similar. And to make an assumption on if for pure liquid, so if I have a pure liquid, we're going to divide this in 2 different categories. So the first one is I write P, so the pressure is not far from the saturation pressure, or changes in the fugacity of a species are very small for a change in pressure going from pressure of the system to the saturation pressure of the species. So if this is things that are worded in your word problem, then you can reduce your fugacity equation to the following. Okay? So you're saying fugacity of a species I is equal to fugacity of species I saturated, which is your fugacity coefficient times your saturation pressure. And again, remember here you need to use Psat. Okay? When I gave you the equation for the activity coefficient before, make sure the pressure you're plugging in is Psat for PU plug-in. Okay? And then Psat, well, that's just Antoine's equation. And then the second category I put it in is if the vapor is an ideal gas in saturation conditions. So if that is something that's worded in your problem statement, then you can say, okay, I have a pure liquid, and the fugacity of that liquid is equal to the saturation pressure. If this is written, vapor is an ideal gas in saturation conditions. Okay? So this will simplify your life much more because this here is just obtained from Antoine. All right, VLE assumptions. So now I'm doing assumptions when you have vapor-liquid equilibrium, okay? So one of the things that you're going to have to start with at all times is this equation up here, okay? This is the ultimate equation. So it is the fugacity coefficient of the species in the mixture times the mole fraction of the vapor times pressure is equal to activity coefficient times xi times fi. Okay, so you always start with that, and then we work our way to simplify based on the information given. So if you are given, if it is said in the problem statement that you have a real liquid, and this is usually said when you have low pressure, okay? And you have low pressure, then your equation simplifies to the following, okay? It's going to be this. So what do you notice happened in that equation? Well, we notice that the fugacity coefficient in the mixture is equal to 1. That is what happened. That's what we changed, okay? And we also notice that the Fi, okay? That is how the equation we started with changed. All right, number 2, if we have an ideal liquid at low pressure, then we can say that the fugacity coefficient in the mixture of the species is equal to 1, and that the fugacity of the species is equal to pi set. Okay, so that is what we have. And then the third equation, the third assumption, is that if the temperature of the species is greater than the critical temperature, so by looking at your table, you're going to use Henry's law, okay? So this here is Henry's law. And honestly, you're not going to be looking for T is greater than T critical. It's going to be usually really, really obvious because you're going to be given Henry's constant. So it's not going to be like, oh, I've got to go check if my T is bigger than my T critical. Like that, it won't ever be that subtle, okay? It's going to be really obvious that you are using Henry's law because the constants will be given. All right, so maybe I'm going to go through what I've just said all over again really, really quickly so that it's clear what the heck is going on, okay? So I started off my video with giving you guys all these equations. So here you're going to notice you have you're going to have a fugacity coefficients, you're going to have fugacity, you're going to have activity coefficients. That's what you see in all these equations I've given you, okay? So the rest of my video explains how to find things like the fugacity coefficient, the fugacity coefficient of a species in a mixture, how to find the fugacity after we find that, okay? And how to simplify equations. That is what my whole video goes through. So the first thing I start with is using PVT relations to help solve these equations. So if once I've decided where I am in this this whole equation box that I've written for you, and I need to find, let's say, the fugacity coefficient, then these are the following 3 equations I'm going to use for when I have a pure species, okay? So when I'm not dealing with mixtures, these are the kind of things I'm looking for. And I explain in the video how to use them, okay? Then if I go to the first table I showed you on the first slide again, and I'm dealing with a mixture, okay? And I need to find the the fugacity coefficient of a species in the mixture to solve for fugacity, okay? You're going to need it to solve for your fugacity. Then these are the equations I've given you to solve for it. And specifically 2 and 3, those are used for binary mixtures, okay? And the way to solve for your constants, not constants, well, they are constants, they just end up being constants. The B12, the B11, and the B22 is what I've showed you right here on the multiple species. So really, you're just using this for finding B12 or B21, which is essentially the same thing, okay? B11 and B22, that is just for the species on its own. So you can use these, it's still going to work, but you can just use the equations I showed you originally. So that would be these ones here under Pitzer method, okay? Beta naught, beta 1, okay? And then, yeah, it's pretty straightforward to find your beta naught and beta 1, okay? Or you could just use these for B11, B22, B12, B21. Doesn't matter, okay? So that's how you find those betas. And then I went into assumptions. So on my first slide again, you decide, okay, where am I a real gas? Am I a pure species? Whatever you decide, equation you need to solve. Here I've given you assumptions that you can use that will simplify your life. So not having to do all these messy equations I showed you. So this is what I went through when I was going through assumptions. Here are all the assumptions you can make to make your life easier and avoid making calculations. Okay? So that's what I've gone through here.